This physics example problem deals with rotational inertia and angular acceleration due to torque. So the object we're going to be working with is compound. We have a cylinder of aluminum, 5.5 kilograms, radius of 9 centimeters, has a length of 12 centimeters. We're going to firmly attach on one end of this first cylinder another cylinder that's also aluminum, mass of 0.3 kilograms, length of 4 centimeters, radius of 3 centimeters. The two cylinders are coaxial. They have a common axis of rotation. Then we're going to take two objects on strings, wrap around these cylinders. The first one is a 0.8 kilogram object. It's on a massless string, and it's wrapping around the smaller cylinder, the second cylinder that has a radius of 3 centimeters. Then we take a smaller mass, 0.3 kilograms, attached to a massless string, and it wraps around the larger cylinder, and it's wrapped in the opposite direction. But it's wrapped around the 5.5 kilogram cylinder that has a radius of 9 centimeters. So these two objects hanging straight down from the strings, they're going to try to rotate the cylinder in opposite directions. And we're on a frictionless axle here. So first, let's calculate the total rotational inertia. We have two cylinders to consider. We have this first larger one, and then we have a smaller one. And they're on the same axis, so we don't have to do any further adjustment. We can just add up the basic calculation for rotational inertia, 1/2 mr squared for each cylinder. 1/2 mr squared is how we calculate the individual rotational inertia or moment of inertia. You might be used to using that term. So let's reveal my picture a little bit here and some of the calculations, but can't be helped. Limited space on the paper. So we have this outer, larger cylinder, 9 centimeters in radius, and we have string coming around here and the 0.3 kilogram object hanging on that string. And then firmly attached on the left side, left face of the cylinder, we have this smaller aluminum cylinder, 3 centimeter radius, and 0.8 kilograms hanging from a string there. I'm going to work the torques such that this counterclockwise direction is the positive direction. So this 0.3 kilogram object here, its force is creating a positive torque, and the 0.8 kilogram object, its torque is going to create a negative torque. But we're still doing rotational inertia. So 1/2 mr squared for both objects, those add up. There is no direction for rotational inertia. It's just the property of the object, 1/2 mr squared for each of those objects, and I get 0.02241. What about the 12 centimeter length, the 4 centimeter length? Those numbers are given in the problem, but I don't see them in the calculation. That's because they don't make a difference. We're rotating on this axis that's dotted line through here, and the length of the cylinder does not change the rotational inertia. It will change the mass, so it might come in that way, but we've already been given the mass of the object. So if you were in a problem and you were given the density and the dimensions of the object, then the length would become important for calculating the volume, and thus the mass of the object you would use in 1/2 mr squared. But for this problem, we were given the mass, so we don't have to worry about L. So the torque. We're trying to calculate angular acceleration. So we have rotational inertia and the torque being involved with that. We've already determined the I value. So what do we have for the two torques? The 0.3 kilogram object times 9.8, that's its force. The lever arm for that force is the radius of this large cylinder, 0.09 meters. So this is torque, force times lever arm. And that's in the positive direction, as I've mentioned up above. Then in the negative torque direction, so I inserted a negative sign here, 0.8, 9.8, and 0.03 meters is the radius of the small cylinder. This torque is trying to rotate the cylinder in this direction, and that's a negative in the way I'm working the problem. It doesn't matter if you want to change this for some other problem. But in your drawing, you should know which way is the positive torque, which way is the negative torque. And now I'm combining these two torques properly. They subtract from each other. And what do we have for the values? Again, you should pause your calculator and verify my numbers are correct. 0.2646 Newton meters for the first one, a negative 0.2352 Newton meters for the second one. And we have a net torque then that is positive, even though this mass was smaller, 0.3 kilograms compared to 0.8. This is the dominating torque, the 0.3 kilograms. Why is that? Its lever arm is 3 times bigger than the lever arm for the more massive object that's trying to rotate the system. So we will rotate around this way. This string will unwind. This string will wind up. So what is our angular acceleration? It's the net torque divided by the total rotational inertia, 0.294 Newton meters. And I just saw that I've left off a zero here, 0.0294 Newton meters, divided by the total rotational inertia, 0.02241 kilograms meter squared. Even though when I was copying here, I miscopied the net torque, I had previously done the division correctly, and the angular acceleration is 1.3 radians per second squared. 1.31 radians per second squared, and it is counterclockwise because the 0.3 kilogram torque, due to that mass, is dominating the net torque. So to find angular acceleration, we needed the I value, we needed the torque value. The rotational inertia comes from the shape of the objects, the mass and dimension, in terms of radius at least. The net torque comes from force times lever arm. The force is perpendicular to the lever arm. As the string comes off the cylinder, it's perpendicular to the radius. So it is a correct calculation, force times lever arm. And we have a resulting angular acceleration. So if you'd like some more physics and astronomy example problems and short lectures, websites that you could go to, they're free. There's just a listing of what YouTube videos are available. Keep practicing your physics.